All right, thank you everyone for joining us today. Today's speaker is Nicolas Kurtovic. He got his bachelor's and master's degree at Universidad de Chile, working with Laura Perez, who I see has called in for this talk today. He is now a PhD student at MPIA, working with Paula Pinea, and he is going to tell us about his recent work looking at substructures in disks around very low mass stars. All right, and then just real quick before we get started, as a reminder, please hold your questions until the end. If you have a short clarifying question, you can type it in the chat and then I will ask it to Nicolas. All right, the floor is yours, Nick.
All right. Well, thank you very much for the introduction, and thank you all for joining. Here in Heidelberg, it's really hot now as we were talking, so at least something is connecting us aside from Zoom. It's hot. And so today I'm going to show you our most recent results on observations of substructures in disks around very low mass stars. Everything that I'm going to show today, it's part of our last submitted paper, which should be on the archive in the short term. I mean, you know how this works. So, oops, sorry, I might be looking to other screens because I have a lot of them here. So let me find them. Yes, there we are. So this will be in the general outline of my presentation. At first, I'm gonna discuss about planet formation and planet detection in very low mass stars. Then I will show you our observations, the results on the dust continuum and also on the gas emission. I'm going to take these results and I'm going to discuss them. I'm going to discuss the substructures that we see, the possible planet formation, and also radial drift. And at the end, I will give you a quick summary with some key takeaway points that you have to remember from this talk. So let's start from the beginning, which is talking about planet formation. So nowadays, we know that planets are everywhere. And missions like Kepler has shown that most of the stars in the Milky Way are host to planetary systems. Also, on the other hand, we know that most of the stars are M-dwarfs, meaning that most of the planetary systems in our galaxy are hosted by a late type star. So with different techniques, such as transits, radial velocities, microlensing, up to now, we have been able to observe some very complex systems around very low mass stars, so like the TRAPPIST-1 system. But we've also been able to observe some giant planets around very low mass stars, such as GJ 3512, which was recently published by Morales et al. In 2019. So the problem with these observations is that when you look at them from the theory of planet formation, it is really hard to explain them and to understand how we get to these planetary systems around the main sequence stars. And the thing is that our current planet formation theories predict radial drift to be very, very efficient in disks around very low mass stars, even more efficient than in disks around moderate mass stars, where the radial drift is already a problem. So here I'm showing a simulation performed by Pinea et al. 2013. So they started with a dust disk that was 30 AU in radius. So you can see that in the absence of dust straps, the extension of the millimeter dust starts decreasing very rapidly. And when you get to 1.5 million years, the extension of this disk is already below 2 AU, which is really, really compact. On top of that, so that's not the only problem, because on top of that, maybe some of you know this meter-sized barrier problem that we have in moderate or high mass stars. So this problem is even stronger in very low mass star disks, because the grains of a few centimeters in size start drifting twice as fast compared to the meter-sized bodies in the moderate mass stars. So to prevent the radial drift from completely depleting the whole disk of dust, we need a strong pressure bump to trap this material. This strong pressure bump would then generate an observable structure in the disks around these kind of objects. So now the question is, do we observe structures in the non-dust depleted disks around very low mass stars? And the answer is yes. I mean, kind of. because we observe substructures, but we have observed substructures only in a few of them. We have some moderate angular resolution observations in millimeter wavelengths that show that, for example, in SIDA1 or in those other two disks which are in lupus, there are some substructures. Maybe you don't see the substructures here in the images, but the thing is that if you feed a simple Gaussian to these disks, you can't explain all the emission that is in there. This is kind of cheating because we know that these three disks are transition disks, so we know them to have cavities. But the thing is that high angular resolution observations of very low mass star disks are not very common. And they are not very common because these disks are usually much dimmer than the disks around high mass stars. So we don't really know how common are the substructures in these disks. We don't know if these disks that I'm showing here, SIDA1 and the other two in lupus, we don't know if they are outliers in their stellar regime. Or maybe the structures are ubiquitous in very low mass star disks, such as they are in the high mass disks. We would like to know if we can find any evidence in these disks of giant planet formation. We are detecting giant planets around M dwarfs, but the theory, from theory, it's really, really hard to explain how the giant planets are forming in them. And finally, can we find any evidence of this expected very efficient radial drift around these disks? So to answer these questions, what we did is that we observed 5 disks around very low mass stars that are located in the Taurus star forming region. These observations were performed with ALMA in band 7, so it's like 0.87 millimeter wavelength, and they have an angular resolution of 0.1 arcsecond or 100 milliarcseconds. With that resolution, since most of these targets are located more or less like at 150 parsecs, we achieve a spatial resolution of about 15 AU, about. So this data that we obtained of the new disks was combined with archival data. And also for sample completeness, we combined these 5 new disks that we observed with observations of SIDA1. So we didn't get new observations for SIDA1, but we took the one that were in already in the archive. So now we're going to analyze uniformly the 6 very low mass star disks that have been observed at high angular resolution in this star forming region. So very important here is to consider that we selected these disks because they are bright. As you can see here in this plot that I'm showing, all the disks that are part of our sample follow a dust to a mass of the dust to the mass of the star relation that is very close to the relation that we know for the transition disks. And we know that transition disks have substructure. So we are selecting this sample to aim for the sources where it's most probable to observe substructures. And that is very important to consider in here. So this is not a non-brightness biased observation. Yeah, there it is. Okay, so with that in mind, let's see what we got. Give me one moment. Okay, so as I told you before, we combined the multiple archival data of band 7 observations of SIDA1 and of the other sources. In this case, SIDA1 was already published before. It was published on PNI et al. 2018, but for this work, what we did is that we combined extra observations of SIDA1, so that allowed us to achieve better angular resolution and also better sensitivity. And with that in mind, those are the results that we obtained. So you can see that all the sources are detected. Some of them look a bit more extended than the other ones. Some of them look very compact. There you have the orbit of Neptune for comparison. So you can see that even though some look a bit more extended than the others, they are all very spatially compact. Just 3 of them are a bit bigger than the Neptune orbit, which has a radius of 30 AU, more or less. And then you have some other 3 that are smaller than the Neptune orbit. So given our 100 milliarcsecond resolution, more or less, we find clear evidence of substructures in 3 of the disks that we have which are the ones that are in the upper row. Well, for the other three, we find that their emission profile is consistent with a Gaussian-like emission. So we don't see any bump or anything. They are just smooth. We don't even resolve like a possible cavity like the discs that I showed from Lupus. So, okay, we have 3 with structure and we have 3 that we do not see substructure. It doesn't mean that structures are not there. And also it's worth noticing that we have 5 disks which have a very, very high signal to noise. Actually, most of them have a signal to noise that is over 300 in the peak. And then we have this guy. So I'm gonna talk about this disk just in the next slides that I'm gonna show now, because I will talk about the gas emission. So just for you not to get lost, I put the names of the disks here in the upper part. So remember that we have 3 disks that have substructure, and then we have 3 disks that are smooth at our current angular resolution. So let's start with the worst one, that is JO415. This disk is very enigmatic. We don't really know what happened in here. From the SMA observations that are well, they are kind of old now. They have more than 10 years, but we were expecting JO415 to be something around 32 millijanskis in brightness. And the observations got only 0.96, so less than 1 millijansky of brightness. In this case, we are combining 2 datasets of ALMA, and they are from 2 separate projects, so they are independent observations, and both of them are consistent within the flux. So it means that, at least what we think is that ALMA is all right. So there might be something that we need to solve in there because of this discrepancy with SMA. But the important thing here is that since this source is much, much dim than what we expected, we don't have enough sensitivity to perform self-calibration. So this source is not only dimmest than the other, but also our sensitivity is much worse. Since the sensitivity is worse, our detection of gas is not as good as in the other sources. So you can see here that 12CO is detected, and very nicely, we see the rotation pattern in the 12CO, nice, but the 13CO just doesn't appear. We are unable to detect it. I really tried. Then we have the other 2 smooth sources. Here, the most important thing that you need to remember, because I'm going to show all the gas that you don't need to remember. I'll just try to remember the key points. And is that since we're observing Taurus, we have a lot of cloud contamination. And it's very strong cloud contamination in some cases. So for example, here in JO420, you can see that we completely lose one side of the disk. We don't observe it. It's just not there. Well, the emission is not there because the gas must be there. And actually the 13CO will recover a little bit of the rotation. So here you see the red shift side, and there you see the blue shift side. But in the 12CO, we just don't see it. And in CEDA7, very nicely and interestingly, we see a non-Keplerian emission. This is like an arc-like emission. And it's interesting because CEDA7, when you look at it in the continuum, it's very small. Actually, this is the smallest source that we got. I'm going to show you later. But then in gas, you see this very extended disk with that asymmetry over there. The asymmetry is not very bright, as you can see it in this image over here. And whenever we calculate the gas radial extension, we don't consider the asymmetry. But still, we are unable to explain what's the origin of this emission. And then in the 13CO, you recover the normal rotation pattern. If we go to the disks with structure now, so those were the smooth disks, and these are the substructures. And here we observe kind of the same. So we have some disks where the extension is very strong in one side of the disk, and the other is relatively nice. For the 13CO, we always have less contamination, but also 13CO, it's less bright than the 12CO. So here you have the emission for CEDA1 and the emission for JO433. Something important here is that whenever we have cloud contamination in the disk, what we do is that we measure the gas radial extension from the side that is less contaminated. That doesn't mean that the gas the cloud contamination is not affecting our measurement of the gas extension, but at least we are trying to mitigate it. And finally, This is our best detection of gas that we have around very low mass stars, and is the gas around MH06. So MH06 is the brightest disk that we have, and it's also the only disk where we can observe the emission of the gas in all the velocity channels. So even though we have a bit of cloud contamination, the cloud contamination is not as strong in the other ones. So we get the whole rotation pattern. Very nicely, you can see that in the 12CO, we recover some, you can see that there is like a vertical emission in here. It's not just a flat disk, while the 13CO is less flared. Also, you can see that in the 13CO, there are some signs of the cavity that we observe in the continuum, but now in the gas emission. If we measure their average, so their azimuthally averaged radial profiles, you can see that here in the 13CO, you see the cavity, you don't see the cavity in the 12CO, and then you have the cavity in the continuum. These radial profiles are all measured from images that have the same beam size. So you can compare the position of the emission. And you can see that the 13CO is peaked closer to the central star compared to the dust emission. And that's something that will be important in the future analysis. Since we have a very, very good detection of the gas, what we did is that we went to the velocity images and we tried to model the Keplerian rotation around the disk, because in that way we could probably, for example, recover the mass of the central star, the dynamic mass. But here we got some problems. So I tried with different velocity images, moment one, we tried generating some images with better moments, we tried different models, we tried different masking, we tried everything, but at the end, we would always get this strange pattern that you can see that is strongly structured. And you see the pattern both in the 12CO and in the 13CO. What we think that is happening here is that our angular resolution is good enough to resolve the vertical structure, so we can see both sides of the disk, and we can see that the upper side and the lower side, but the signal to noise is not enough in the channel maps to disentangle this emission. So then when we create these when we create these velocity images, we have emission of both sides in the same image, and then we just can't fit it because there's a strong correlation between the central mass star, the inclination, and the vertical structure. So for now, we didn't go deeper in this work. For the future, it would be nice to model this and try to recover more information, because the information is there. I mean, you have the information of the central mass star, you have the information of the vertical structure, but for now, we will just care about the gas radial extension, and we're gonna leave it there. So for a future work, we will go back and try to model the gas. Probably we will need something more complex, not just looking at the images, but probably something like UV modeling the gas, which has to be done. So, okay, those were the observations, and now let's go to the analysis. So let's start, let me move something here, one moment. Okay, so let's go to the substructures. So now here you can see again the images. One important thing that you have to notice from the images is that the extension of the dust and also the size of the structures are comparable to the beam size, as you can see. So if you try to analyze the structures from the images that we generate with clean, then you're going to be biased towards the beam size. So the good approach to analyze these substructures is not analyzing them from the image, but analyzing the visibilities itself. So that's what we did. I'm gonna first show the smooth disks because they are the most boring ones. So you can see that we just fitted a single Gaussian. The single Gaussian is a very good model both for CEDA7, sorry, and for GO415. CEDA7 is the smallest disk that I told you, and GO415 is this special guy that was much dimmer than expected. In the case of GO420, you can see that we have some residuals, which at the beginning was interesting. So I tried more complex models, something like a ring, for example. But even though it's hard to notice it from this image, the emission that we have here in the residuals is not axisymmetric. Actually, it's not centrally picked. This is not the center of the image. So here we have the two options. We could try to model that emission with the risk of over-modeling the emission that we have in the disk, or we could just stick to the smooth Gaussian. In this case, the emission of the original data is over 300 in signal to noise. And after the subtraction, you have these 5 sigma peaks. So the residuals are still very, very low in contrast compared to the overall axisymmetric emission. So we are still considering this disk to be smooth. Still, you have to notice, for example, here in CEDA7, you see that there is some emission that we're not describing with a Gaussian. You see this emission in the residuals of here. So there are hints of substructure in these disks that we are just unable to describe. Higher angular resolution will be needed, but yeah, it's nice. It's nice to see that even the disks that look like smooth, they may have something. Actually, they probably do. And then for GO415, the important thing is that we resolve the emission. So you can see that when you go through the baselines, the emission is not constant, but you can see that it decreases. Then we have the sources with structure. So here we have CEDA1. You can see that CEDA1 doesn't have the same long baselines that we have for the other ones. That's because we're just combining the archival data, but the resolution is still similar. In the case of CEDA1 and MH06, what we do is that we just model them with a broken Gaussian, an asymmetric Gaussian. So it's basically a Gaussian that has different widths on each side of the central peak. You can see that in the case of MH06, we have some asymmetries. Now these asymmetries, they are well over 5 sigma, so there is something in there that we are not describing. And again, same as the GO420, most of the emission still follows this axisymmetric profile. So we're going to stick to the profile that we have. But there is some asymmetric emission in there that we are not describing. It's low in contrast, but there is an asymmetry. And then for GO433, it was really, really challenging to model it. And because of that, I want to advertise this package that for me was very useful. So this disclaimer, I have no participation on the design of this package or in the paper. I just want to advertise it because I think it's a very good contribution for the community. So this is a package that is called Frank. What Frank does is that it takes the visibilities of an observation, and then using Gaussian processes, it finds the best radial profile that fits the data. So it's a 1D fit. So what Frank gives you, it's a non-parametric axisymmetric model of your source. And depending on the signal to noise of your data, this model can achieve better than nominal resolution. And you can see structure that you couldn't see in the images, but the information of the structure is still there in the visibilities. There is something that I don't like about this package. It's probably because it was just released in May. And it is that because it uses Gaussian processes, sometimes you get these very low amplitude oscillations that they are in the whole radial profile. So you still have these low amplitude oscillations in this part of the profile. So for now, what we did is that we used Frank to guide our parametric models, but we didn't use it to describe the radial profile. So in this case, Frank is telling us that there is a centrally peaked emission, and then there are something like 2 rings. So that's what we tried. And then we got this model over here that you can see that fits very well to the data. And for this one, we tried everything before Frank. We tried, well, one Gaussian, a Gaussian with a ring, a Gaussian with an asymmetric ring, and nothing was working until we tried this. So for me, at least, it's very, very nice how you can go from, literally, it's like you can go from a potato to a multi-ring system. So yeah, when we model it, some of the workers do not choose to have this dip over here. So it is not completely clear if the separation between this ring and this other one is a real separation. Maybe this ring over here is just like a shoulder for the main ring. We don't really know with this angular resolution, but still, I think it's a very good model. So, okay, so these were the images that we got before the modeling. And now what we're going to do is that we're going to analyze everything on the models that we got. And that's because, well, one or models have better angular resolution because it's like infinite resolution. We are not, again, describing all the substructures that these disks have. They probably have more substructure, but at least the overall emission, the overall morphology of the disks should be very, very similar to the one that we are modeling. It shouldn't change if you increase the resolution. So for me, this transition is very nice. So we go from these images to these ones over here. And this is what we are going to analyze from now on. Okay, so let's talk about the planet formation in these disks. Whoops. Okay, there we are. Give me one moment. I need to move my notes. Okay, so first of all, we know that planets interact with their surroundings. And so their formation will affect the dust and the gas distribution on the disk. And possibly this change in the gas and dust distribution will create the substructures that we're trying to observe. So in this case, we have 3 disks that have substructures. And what we are going to do is that we're going to try to understand what's the process that is originating each one of these observations. Now, if we assume that the emission of the dust in these disks is optically thin, and if we also assume that the temperature of the dust is 20 Kelvin constant with radius, then we can try to estimate what's the mass of the disk, and we get that the mass of the dust is around 10 Earth masses for each one of the disks. Well, 12, 8, and 14, respectively. And then if we assume that there is a gas to dust ratio of 100 to 1, then the mass of the gas is around a few Jupiters. So you have 3 Jupiters, 4 to 5 Jupiters. So they are not very massive, but they have a good reservoir of mass. So let's try to see what's causing the substructures in each one of them. First, let's start with MH06. Very nicely in here, you can see that, well, it has a cavity. You could also see it in the continuum image. This cavity has a size of 10 AU. And very nicely, this is one of the smallest cavities that we have observed, together with the cavity in AS205 South. So the cavity in AS205 South has a size of about 3 AU. We didn't UV model that one. We were just measuring it from the image. And in this case, this one has 10 AU. And I compared it with the other transition disks, and I think that these are the 2 smallest. So, okay, so there are several processes that could explain this cavity. I'm listing them in here. But long story short, what we think that is the most probable explanation is the embedded planet. Once we get this paper published, you can see the whole discussion about each one of these processes. So I'm just gonna give like a one-line summary for each one of them. There are some observational reasons that make us think that maybe these processes are not the ones that are originating the cavity. So for example, for photo operation, we don't see a 12CO cavity between all the reasons. And the binary companion has never been observed, even though this disk has been observed a lot of times with spectroscopy. Dead zone could also produce these kind of cavities, but in this case, the gas predictions that we have for dead zones were not met with the observations that we have. So yeah, maybe the cavity is a combination of different mechanisms. We are not excluding any of these ones, but most probably it's embedded planets. Now, this is also an unfair comparison because it's really hard to rule out an embedded planet. Like, it's really hard to get to the point where you can say, okay, no, this is not an embedded planet. This must be another thing. So yeah, it's an unfair comparison. Planets are really, really flexible. But let's assume for a moment that this cavity is being produced by a single planet. So if we assume that, we can locate this planet at 7 AU, and then we would need it to be between 0.2 to 0.3 Jupiter masses to generate that cavity that we are observing. So just for you to remember, 0.3 Jupiter masses is about 1 Saturn mass. So it would be like a Saturn carving that cavity over there. For SIDA-1, the overall emission that we detect is not that different from the same analysis that was done in MPIA 2018. So we're not changing the results in there because it's not worth it. It was already done. And in this case, a planet located at 15 AU, also with 1 Saturn mass, could explain the cavity. And finally, in JO433, what we did is that we made an estimate by using the heel radius of this candidate planet located in the gap that is between the central emission and the first ring. And this planet would need to be around 10% of Jupiter mass, or a third of a Saturn mass. So yeah, well, that's very nice. Let me move my notes again. Okay, so for all the sources, we also checked on the ice line location, because maybe the ice lines were producing some substructures. But in these cases, since they are very low mass stars, the ice lines are all located very close to the star, and we don't have the angular resolution to resolve any of the locations of the ice lines. So yeah, ice lines are probably not the responsibles of these structures. So, like as a conclusion of this planet formation part, based on the conservative measurements of the disk masses that we have, because they are conservative, the dust mass is probably higher. Based on the substructures that we are detecting on each source, we conclude that these disks show some evidence of possible ongoing giant planet formation. Now, this is, of course, just a first analysis of the observations. In this case, we are not considering, for example, that multiple planets could be producing the substructures. So in the future, a better characterization of these protoplanetary systems needs higher angular resolution, and probably we will also need some hydromodeling. But up to now, at least this is a very good estimate. It's good to see that the brightest disks and the most extended disks around very low mass stars could be, in fact, forming these giant planets, or these complex planetary systems that I talked about in the beginning, like TRAPPIST-1. So let me move. Okay. So as for the compact disks, well, you can see that they are all really, really small when we calculate the 90% radius. So see the 7, again, for the third time, it's the smallest one of our whole sample. It's just 13 AU. And like, puzzlingly, see the 7, it's smaller than JO415, even though JO415 has considerably lower a lower mass compared to CEDA 7. So here you can see that CEDA 7 is 6 Earth masses in dust content. That's a good dust content. JO420 is 6 Earth masses too. And then JO415 is just like 2 Mars masses. This is like very, this is considerably less massive than the other ones. And still somehow it's managing to be radially extended, which is strange. So now let's go to the radial drift part, which is gonna be the final section, so don't worry. Okay, so if we compare our results with other Taurus, let me turn on the light. Okay. So if we compare our results with the other Taurus disks, you can see that in fact, we have the brightest disks in their stellar regime. We didn't choose this one because this one has a very, very, very high extinction magnitude. And then this other one is just an upper limit. So we didn't know if it was this bright or this bright. And we were hoping for JO415 to be much brighter than what it is. So you can see that they are the brightest ones in their stellar regime, and they are also following more or less the same trend that we already knew for the Taurus region. Now here's where it starts getting more interesting, is that when we look at the size-luminosity relation, you can see that the very low mass stars follow, well, the same trend that we already knew for Taurus. So here in blue, you can see the trend as it was fitted by Handler et al. 2020. And in green and in red, you can see the fits that we did with the very low mass stars. So in red is the fit for the trend, considering only the bright disks around very low mass stars. And then in green, you can see the fit when we also consider JO415. So yeah, well, you can see that they are both, very close to the Handler et al. 2020 relation. But the difference between the green relation and the red relation is about 1 sigma. So it's unclear if this difference is significant or not. At least there is a difference. But also we need to consider that GEO-415 is the only source that we have in this luminosity regime. So that's a problem because we might be doing like a low number statistic. By now, it isn't clear if GEO-415 is just a very extended disk for its luminosity, or if the relation is not the same along the whole luminosity range. So maybe there is a relation for these disks that are brighter, and then there's another relation here, we don't know, or maybe it's just the same relation and GEO-415 somehow it's just manages to stay extended. It's still a very interesting source because there must be something that is keeping the dust so far away from the star. So yeah, it's an interesting source to take a second look in the future. Now, finally, if we compare the gas extension to the dust extension, you can see that our sources, or at least the bright ones on CDA7, they all have a ratio between the gas and the dust extension that is well over 3.5. There were two publications by Leon Trapman, so one in 2019 and one that was in 2020, where they discussed that if you see a source with a gas to dust extension ratio that is over 4, then it means that there is no single mechanism that can explain this difference in the size without considering the radial drift. In this case, when we measure the gas radii of each one of our sources, what we do is that we measure it, one, from the image. We are clipping the images at 3 sigma. And you also have to consider that we have cloud contamination. And the cloud contamination is stronger in the velocity channels that are closer to the central velocity. So we are missing the emission that is farthest away from the star. So it doesn't matter how you measure it, our measurement is probably the most conservative. So for us, at least, these are conservative ratios for the stars that we have. They are probably, if you measure them in some other way, you would get over 4. So what we are seeing here is evidence of strong radial drift in most of our sources. We can't confirm this in these two sources over here. This one over here is the special guy, GEO-415, the one that is the dimmest. And then the other one is GEO-420. GEO-420 is the one that has the strongest cloud contamination. It's the one where we completely missed one side of the disk, while GEO-415 is the one where we have the least sensitivity. So probably the ratio between the gas extension and the dust extension is higher for both of them, but the data that we have is just not allowing us to measure it properly. And that's something that should be considered in the future. And actually, the cloud contamination is something that at some moment we should try to solve somehow. Well, we can't just recover the emission that was extended, but again, maybe with some more complex modeling on the data that we have. Okay, so that was all the information, and now we can go to the final summary. So here you have the key takeaway points of this work. First of all, the disks around very low mass stars have substructures. We find that annular substructures are the most common substructures in these objects, but there is evidence of asymmetries in these disks. It's just that we're unable to describe these asymmetries with the current sensitivity and angular resolution. So more observations of these objects are needed. Second, the properties and the substructures that we find in these objects do not exclude the giant planet formation, as we have observed giants around main sequence stars. So we still need to explain the theory behind the formation of these objects, but at least in the observations, we have that it is possible. We also find evidence to claim that our sources have experienced very efficient radial drift, and somehow this radial drift has now stopped because we are seeing dust in the sources. And finally, this first sample of very low mass stars highlights the need for more deep, high angular resolution observations of these objects. We need more observations of a bigger sample if we really wanted to understand how is the planet formation process in most of the planetary systems in the Milky Way. So thank you very much.
All right, thank you so much, Nicholas. If you have a question for the speaker, please use the raise hand button under the participants tab. If you're unable to unmute yourself, then you can put your question in the chat and the organizers will read it out. All right, Ninka.
Hi, Nicholas. Nice talk. Really great results. So I have two questions. One is actually just clarification. You mentioned that for this one source, there is the SMA data had predicted that you would have bright CO emission, but you had it much dimmer. Yeah. What kind of SMA data are we talking about? Is that like unresolved emission, or is that, I assume this was old CO observations?
Actually, the SMA didn't observe the equivalent of ALMA band 7. They observed in 1.3 millimeters, so not 0.1 millimeter.
Okay.
0.9, sorry. So this expected 32 millijanskis was extrapolated from the equivalent to the band 6 of ALMA. So that's something that could introduce some noise. So you can see that the error bar is actually 15, it's a lot. Mm-hmm. And what we think that maybe happened in there is, we know that there is some radio variability in some sources. Maybe this is one of those, like for example, like in Proxima, that you got this that huge flare. Maybe something like that happened. This data was published in it was Andrews 2010.
Probably Andrews 2000, yeah, or even
I don't remember if it was 10 or 12. So yeah, it comes from there. And then I think that they have used similar data in some other studies, like in Tripartite 2017. I'm not sure. But yeah, well, in this case, we have two different independent ALMA observations. So I'm quite convinced that this is the correct measurement. But yeah, there is something in there that has to be solved.
Right. No, but it really was based on old CO observations, not extrapolation from the continuum or something.
No. I think it's extrapolated from the continuum, but it's extrapolated from an old continuum observation. So.
Oh, okay, okay. So this was a continuum. So yeah. So even the continuum is dimmer than expected. I see. Sorry, I thought it was extrapolation from the CO, and that surprised me. But
no, I don't think so. I think it was from the 1.3 millimeter emission.
Right. I mean, there's for younger sources, there is evidence for millimeter variability in the continuum as well. So that's definitely possible, which is also linked to accretion. Yeah, well, I'll read about it in your paper to see. And my other question was about your. So you mentioned that the 13 CO gap in one of your transition disks was smaller than the dust gap. And you said you would come back to that later. I don't think you did. Okay. I mean, I worked a lot on this, so I'm curious what else you did on this topic.
Very quickly, like in 2 lines. So there is some evidence. I think this was also a Stefano Facchini paper with Paola. There is some evidence that from dead zones you would expect the millimeter peak and the scatter light peak in the same position. And we know that scatter light follows the gas. So we would expect the gas to be very close or in the same position as the dust. And in this case, we can see that we have a consistent separation, which is expected from the pressure bumps that we have from planets. So that's like another reason for the embedded planet.
Yeah. No, I mean, like I said, I worked on this. Like my 2016 paper is showing this exactly for a number of larger transition disks. So I was wondering if you did some like planet disk interaction modeling, or like you mentioned your derived planet masses. I was wondering
not for this. We didn't model it. We just estimated to see what was the order of magnitude.
Okay, but the planet mass was not based on this ratio, basically.
No, we didn't use the CO to calculate to estimate the planet mass.
Okay. Yeah. Okay, thank you.
Oh, thank you.
All right, Rich.
Hi, thanks. That was a really nice talk. I was wondering about the systematic sort of residuals you're getting from the rotation map fitting. How well constrained the inclination is here, because those sort of 6-spoke residuals are exactly what you'd expect for a misspecified inclination. Even if it's only 1 or 2 degrees off, that's exactly what you would find. So I was wondering whether you tried with letting the inclination vary a little bit, or whether that didn't fit as well.
Yeah. In fact, I tried not fixing the inclination or changing it a little bit. But if the inclination was let free, it would just find like a very weird inclination. In this case, I can't remember the exact number. It was something like 60 degrees in inclination. And then if we let the inclination to be a free parameter, it was something like 30 degrees. So it didn't make any sense.
Yeah, that's
so currently what I'm trying to do is like this Keplerian masking for the images. So in the future, I would like to have like this same Keplerian masking, but instead of being a masking, I would like to try to fit each image on each one of the channels that we have for ALMA. That's gonna be really time consuming. So I don't think I'm gonna have something like that soon, but in the future, I would like to try that.
Okay, cool, thanks.
All right, I have a question. So when you were fitting the substructure for JO433 and you ended up you having to use Gaussian processes and you ended up with this very narrow, bright ring, how well constrained is that? Like, so clearly from the visibilities, there must be something going on, but how well can you constrain whether that's a bright and narrow ring or like a more extended feature?
So in this case, well, we're using a parametric model, and the parametric model is a centrally picked Gaussian with 2 Gaussians following. Some of the, as I mentioned, some of the workers were choosing to merge the 2 Gaussians into a single one, but this one would never go inside the more peaked Gaussian. So from the modeling, it is unclear if this is a very narrow ring with another ring that is more extended, or if it is a single ring that then just fades very slowly. That's unclear. I can't confirm, even though I think this separation is real, I can't confirm that it is. But definitely the separation, this very high contrast between the first ring and the central emission, that contrast was chosen for all the workers. We know that the workers in this kind of fits, they usually do not cover the whole error margin that they should. But I think that consistently this gap was more or less the same contrast and in the same position. So I think I'm quite convinced of this first ring being very peaked. And then it's just the outer part which is not completely clear.
Okay, thank you. Laura, did you still have a question or are you good?
Hi, yes. Nice talk, Nico. Good to see you.
Thanks, yeah.
The question I had for you was, you were measuring the disk masses from the dust masses, right? And then extrapolating with a gas-to-dust ratio. But you also showed that a whole bunch of these disks have very large outer disk radii in the gas. So do you get a sense how much these measurements will change if you really include, you know, these large extents? Because it seems like the dust with all this radial drift is tracing a different part of the disk.
Yes, that's actually a very good comment. We don't have an estimation to see what would be the impact of the differences in the gas extension. I guess that we should try to start modeling the emission, not modeling like the visibilities, but modeling the hydro modeling to try something like that. But yeah, up to now, we don't have those kind of estimates. So these numbers over here are just like estimates to have like an order of magnitude in the mind. But yeah, to have if we want to get a better estimate on what's the true mass of these disks, we will need to do some hydro modeling.
Thanks.
No, thanks to you. It was a very good comment. I'm gonna write it somewhere.
All right, Nika.
Yeah, sorry, I just had thought of another question kind of related to these dust masses, because I was a little confused when you say that these disks follow the trend of the size dust mass relation. Because at the same time you selected them from following this basically being the brightest disks around very low mass stars. So how is that possible that because that seems inconsistent with each other? I know these are two different relations, but they're still, yeah. How do you connect that?
Oh, well, if we look at them, for example, here, where we look at the mass of the dust compared to the mass of the star, you can see that they follow the overall trend, but they are on top of
Oh, okay. It's not, yeah,
stellar regime.
Because I remember the Paula's work of indeed this trend of dust mass and stellar mass, where that basically the transition and ring disks, they are.
Yeah, you would expect it to be higher compared to the others.
Yeah, so I'm just a bit so maybe these are still outliers within that relation. Like these are not that bright if you compare them to the other disks in Paula's relation for the transition disks or the structure disks.
For those, so yes, well.
Sorry. Maybe yes. this is. I'm not trying to corner you here.
No,
I'm just a
they
bit worried about your choice of disks. Like, how significant is it really that they are within? Because you choose 5 disks and you try to draw conclusions from that. But I'm wondering how much of that is affected by your sample choice. That's really what I'm aiming at.
Oh, so yeah, no, totally. This is totally biased towards the bright disks. So you can see that it follows the overall trend. Like they are not located like here, for example. So you can see that it's not like they are decreasing now, and at some moment it takes a big step. So yeah, they follow the overall general trend. But yeah, they are the brightest ones.
I see.
So yeah, like every conclusion that we draw from this sample, it's only for very bright disks, except for J0415, which is the weird one of the sample. And then in the other cases, for example, here, if you look at the luminosity, since the luminosity is in the X range, then yeah, these are the bright ones, and they follow like the same relation that we have for the bright ones. But the problem is that we don't have the coverage in there. So yeah, that's something that should be considered for next works. But no, as you say, everything that we get in here is just valid for bright disks around very low masses.
Right. Yeah. I mean, ideally, we would like to have the high resolution observations of all low mass disks, which is one of your recommendations at the end.
At infinite sensitivity.
Yeah. So just having these 5 disks, it's.
Yeah,
I think you cannot really draw conclusions on the general sample because of that. So
definitely. So this is just so, for example, as with the giant planet formation, we're not claiming that we are in fact forming giants. So it's not a confirmation, but we're showing that the conditions are met. So that's something, for example. It's not that all of them have these conditions, but in some of them that happens. So yeah, this is like a beginning of the study on very low mass stars.
Yeah. Okay, thank you.
All right. Any final questions? If not, then I would suggest that we all unmute and thank Nicolas for a really excellent talk.
Thank you very much. Thank you for the invitation and for the opportunity. Okay, so I'm gonna stop sharing.